no secret hidden mics. Just the two of us, well, the three of us, the 12 of us. That'd be the 10 beers, you and me, and I'll tell you all the jokes that you need. So if we are about ready, Ted?
Still got about 25 seconds.
Now, I'm no mathematician.
TED time.
Oh, TED time.
No. Public, yeah, if not.
And tonight, I have you know, will probably not be the 24th best night of my life. But last night was the 23rd best night. Without a doubt.
So tonight, is it going to be the 21st or the 25th?
Not even going to get in the top 100. I got no place to stay. We're good. Okay, we're live.
All right, so there we go. Yeah, it's a shame all you people watching this on video missed that because that was just really friggin' hilarious. So, damn it. Okay, so we've got Joel Voss up here now, so please let's give him a big warm Toorcon welcome. Let's bring him up to the stage.
Good afternoon. I want to talk to you about relationships in code, but since I got here, I've been learning how great an audience Toorcon is. So I was thinking, that my original talk was a lot more basic than it should be, and I thought I'd leave it up to a show of hands who wants to watch or participate in the advanced talk rather than the beginner talk. Show of hands? Okay, I thought that was it. So let's switch over. So I'm going to be talking about advanced code relationships, and the idea is that whenever you find a bug, whenever you find a vulnerability in software, there's relationships all over that, and really there's some interesting relationships that we can look at and gain some ground. And I'm going to be making some interesting assumptions, and I'm going to say some things that you as static analysis people and coders, programmers, security people might not agree with. So if you disagree, just raise your hand briefly, or if I'm boring you, go ahead and give me a thumbs down. So let's take a look at some code. I'm going to be releasing 2 bugs that I found in my work. So where do you start when you start looking for bugs? Well, the easiest one to find is sprintf. If you do a grep of your code or find in files for you GUI people, you end up finding all these sprintfs. And these sprintfs have a specific issue with them that everybody knows about, except when it's their code. They haven't actually looked properly, and so BlueZ is the Linux Bluetooth system. There's a user-land program called Dundee, which does dial-up networking. It just happens to do a sprintf on %d, which it takes from the command line, which I'm putting in this rather large negative number here. And so then when you connect to it, it'll overflow. And so the relationships that are involved with this specific issue is that you have an array, and that array was allocated 10 bytes. So here's the array, and it was allocated 10 bytes, and it depends on this sprintf working as it was designed. And that depends on the input, the integer, the channel, and the channel depends on the command line argument. Of course, that's a very minor bug because it requires either suid, Dundee, or it requires user interaction. So let's look at vulnerabilities in general. So we all know the 3 big vulnerabilities that we normally find. The buffer overflow due to an array index. And then there's null dereferences, where you have some conditional code that allows you to dereference a null pointer. And then you have the buffer functions, like I said, sprintf and so forth. So let's look at the specs of array buffer overflow. You probably understand that every buffer is allocated, and it's allocated here. It is written here. And so when you're on the stack, this is how you allocate, and this is how you set any buffer. And in this case, can anyone see what's wrong with this code? So you have this function here that's returning a variable. Just shout it out if you see it. And you have this set here. Well, so this buffer here is being allocated here and deallocated here because it's on the stack, and then it's being written here. And this doesn't give you a compiler error. If you return buff instead, it does give you a compiler warning. So let's, the heap doesn't have the the deallocate on out of scope, so you're able to pass your variable quite far from its origin. You can actually pass it through 100 functions if you like, through a recursive function. But so if you're going to find an issue with a piece of code, like a buffer indice issue, you have to figure out the buffer allocation and the index. So here you have the allocation, here you have the index. And so let's take a look at the two simplest cases. The simplest case here I've graphed here is where you have a variable a, which is a buffer, and it's allocated 24, and it depends on there being 24 bytes. Of course, it says 23 because that's the index. And you can have more complex relationships. Like this, we add the variable I, and I depends on 2 and 24, less than 24. And so you can see the same thing occurs here. You just have to follow it longer and to 2 places instead of 1. Does that kind of make sense, the graphs here? What I'm relating in the code? It should be pretty obvious if you've seen any obvious issues in code. Here's an interesting one where we're actually passing this allocated buffer to this function, and then we're doing the loop over here. This function actually doesn't know how large the buffer is that it's modifying, and so that's interesting. But if it doesn't overflow, then we don't really care. So let's continue on. Real code has a bunch of relationships, and that makes our job difficult. Complexity breeds difficulty in static analysis. If you look at like BlueZ, it has 104,000 lines of code, and to vet all that, you have to do a lot of work. And so that depends on the derefs, the arrays, and for loops, buffer calls. There's a bunch, and so to vet each one, you're going to be spending time. And so my program tries to reduce that and tries to decide what should be done. If you're thinking that it's going to end up looking like this, that's not exactly true. That I just created this to show people what you shouldn't be expecting. So if you think about what we just said every time you pass a pointer to a function, you're wondering whether that was allocated, whether it's null, what are the properties of this buffer? And here you're dereferencing it, right? So you assume that buffer this pointer can never be null. And same here with this buff, right? So in this example, we have Timidity. It's the latest version of their software. It does MIDI in Linux. It's a software synthesizer. It should be installed on every machine. And so this is